Hello, and welcome to Settle the Stars. Episode 12, The Moons of Jupiter. Hey folks, this is Alexander Winn. Today's episode is special. We'll be taking a break from our planet-by-planet exploration of the solar system and instead embarking on a whirlwind tour of the complex and dynamic system of moons orbiting Jupiter. These worlds range from rocky to icy, and from planet-sized spheres to small lopsided mounds, with a variety of compositions and characteristics that have scientists scratching their heads to this day. There are tantalizing hints of rich resources and potentially life-supporting regions that bode well for possible human exploration, and we'll be taking a close look at many of the major objects in anticipation of what those first explorers might encounter. Much of the information we'll discuss today is the result of the extensive Pioneer, Voyager, Galileo, and Juno missions undertaken within the last century. We discussed these missions in more depth in the last episode about Jupiter, so if you haven't checked that out yet, you might want to now for some context. All done? Okay, welcome back. Let's talk about the moons of Jupiter. Viewed as a whole, there's a lot of ground to cover. There are currently 79 known moons in orbit around Jupiter, belonging to several groupings. The first is the regular satellites, which all have prograde orbits. That means they move in a counterclockwise direction when viewed from above the North Pole of Jupiter. That's the same direction that most things in the solar system are moving. Innermost are the Amalthea group, with 4 members, which help maintain Jupiter's small ring systems. Further out are the main group of 4 large Galilean moons, Io, Europa, Ganymede, and Callisto. The other broad grouping is the irregular satellites. These are much smaller and orbit much farther away, often on retrograde, eccentric, or non-circular orbits. There are some subfamilies within this group that share similar orbital patterns and provide hints of a shared origin. Most of these satellites have only recently been discovered, either by closer observation of one or more of the visiting spacecraft sent from Earth, or more commonly by advanced telescopes here at home. The 4 largest are known as the Galilean moons, named after their discoverer Galileo Galilei in 1609 or 1610. His discovery marked the first observation of a large body in orbit around an object not the Sun or Earth, which directly contradicted the prevailing Ptolemaic geocentric world system and earned him the scorn of the Catholic Church. A close second-place prize for the discovery of the 4 moons is enjoyed by Simon Marius, who observed the same 4 objects only 1 day after Galileo. He and Galileo also had some hilariously vicious animosity, with Galileo describing him as an old adversary and a poisonous reptile and the enemy of all mankind. Then, as now, science is a full-contact blood sport. Any mythology buffs out there will recognize the names of the Galilean moons as Zeus's beautiful favorites and recipients of the Greek god's interest and sometimes questionable affection. This convention has continued as newer moons are discovered, but even Zeus's notorious exploits have a limit. Since 2004, the names have included his descendants as well. Additionally, all satellites named since Eupori that end in A or O are prograde irregular satellites, and names that end in E are retrograde irregulars. Any little hint that will help us as we navigate these moons today will be welcome, I'm sure. Before we start moon hopping, let's set the stage a little bit. After all, it's not as though early explorers will be able to just zip straight over. There are many challenges in even getting to Jupiter that are worth considering. First is the distance. From Earth, a flight to Jupiter is no puddle jump. NASA scientists have some experience in sending objects to Jupiter by now, and current technology places the journey somewhere around 6 years to complete. 6 years just to get there at all. The current record for continuous spaceflight by a human is held by Russian cosmonaut Valery Polyakov with a total of 437 days. That's about 1,752 shy of a trip to Jupiter, to say nothing of the mission and the trip back. So the lucky explorers selected for the first Jupiter visit will almost certainly be test subjects for long-term spaceflight in their own right. Spaceflight boredom is far from the only challenge, however. There's also the matter of the asteroid belt, a massive area of asteroids orbiting the Sun in a wide belt between Mars and Jupiter. Though the asteroids within are much smaller, the entire belt's mass combined is about 4% of Earth's moon, and the belt is much more sparsely populated than science fiction would have you believe. Even small objects can cause serious damage to a passing spacecraft. Even a pebble or a grain of sand is enough to do serious damage when you hit it going 35,000 miles an hour. And while we're dodging objects, there are others we'll have to be sure to avoid as we approach Jupiter. The Trojans. By that, I don't mean the popular brand of condoms or the most excellent USC football team. No, the Trojans are asteroids that orbit within a planet's orbital path, sheltered in gravitationally stable locations, either just ahead or just behind the planet as it circles the sun. You can think of them sort of like debris caught in a planet's wake as it travels around the sun. Other planets have them too. There are Neptune Trojans, Mars Trojans, and even a recently discovered Earth Trojan. But Jupiter has by far the most, possibly more than 2 million that are larger than a kilometer across, which is way more firepower than you'd need to end a spaceflight mission. As spacecraft move between planetary orbits, they often transition between them by merging into them from outside the orbit, a bit like entering a highway from an on-ramp. The difference in this case is that the highway we're merging into is jam-packed with traffic, so a little extra care will be required to make sure we arrive at Jupiter outside of rush hour, so to speak. But by far the greatest danger on the journey to Jupiter will be radiation. Radiation is always a concern on flights in open space, since leaving the protective shield of Earth's magnetosphere leaves spacecraft vulnerable to charged particles from the sun and outside our solar system. The good news is, our destination Jupiter has a nice large magnetosphere of its own, like Earth's, but supercharged. The bad news is that the planet generates its own radiation fields that are very large and very powerful, enveloping many of the closer moons and complicating human exploration. But once we arrive in the Jovian system for our virtual journey, thankfully without any holes from tiny asteroids or damaged DNA from harmful radiation, we can begin our exploration of the moons. Starting closest to Jupiter and working our way outwards, we begin with a small group of 4 innermost moons. These moons are, in order, Metis, Adrastea, Amalthea, and Thebe. They might not seem particularly notable as tourist destinations given their small size. Adrastea is smallest, about 16 kilometers across, and Amalthea is largest at 167 kilometers. But they have a special position as originators and maintainers of Jupiter's faint ring system. Metis and Adrastea keep the inner ring replenished with dust and ice, while Amalthea and Thebe each keep their own faint outer ring. The really spectacular ring show will have to wait for our future episode on Saturn, but a flyby of these moons from behind Jupiter would allow the sun to illuminate them as faint halos stretching from one edge of the sky to the other. As we head farther away from Jupiter, we'll encounter the first of the 4 Galilean moons, Io. In contrast to the glowing welcome of the ring systems, Io makes no effort to be inviting. It is one of the most hostile environments in our solar system for humans to visit. But that almost makes it more exciting, right? Io is named for a mythological priestess of Hera who became one of Zeus's lovers. Until the Voyager missions revealed stunning details of the planet's surface, very little was known about this world. Io is slightly larger than Earth's moon, and shines brightly with yellow, orange, and brown hues pockmarked with craters and volcanoes. A moon of this size, so close to Jupiter, experiences intense tidal forces, being constantly crunched and twisted by the gravity of Jupiter and the other Galilean moons with every rotation. You can think of it a bit like Play-Doh or gum. The planet is constantly being squeezed and worked and kneaded, which keeps the interior hot and fluid instead of letting it cool off and solidify. The result is a constantly churning and shifting interior, creating the most geologically active object in the solar system. Thousands of volcanoes eject gigantic plumes of sulfur and sulfur dioxide hundreds of miles above the surface, and intense uplifting events have produced massive mountain ranges taller than Mount Everest. Lava flows can reach over 300 miles long and spread across the surface, which is composed mostly of silicate rock. There is a thin atmosphere, but it offers little relief in the form of moisture or clouds. Water simply doesn't exist here. Io contains the least water by percent composition of any known object in the solar system, probably due to Jupiter's heat during formation being great enough to drive water molecules away from the nearby moon. The ultra-thin atmosphere consists mostly of sulfur dioxide ejected from volcanoes, certainly nothing you want in your lungs. I mentioned radiation earlier, and Io is definitely the moon to be most concerned about while visiting. Io's composition and location give it an interesting role to play in the magnetism and radiation around Jupiter. Scientists are still studying these complex interactions, but from what we have observed, the dust and molecular compounds surrounding Io from its volcanic ejections interact with Jupiter's magnetosphere to produce some interesting effects. One is a giant torus, or a donut-shaped cloud of plasma surrounding Jupiter, consisting of ionized sulfur, oxygen, sodium, and chlorine from Io's atmosphere. The second is what has been called the Io flux tube, an electric current surrounding the moon generated by the passage of Io, along with its cloud of dust, across Jupiter's powerful magnetic field. This current is strong enough to produce an aura in Io's atmosphere, as well as Jupiter's polar region, called the Io footprint. Scientists have also found during the Juno mission that the position of Io relative to Jupiter could have a powerful effect on the strength of radio transmissions from the spacecraft. Before we head to the mountaintops to get a better view of the magnetic auroras, you should know, temperature works a little different than we're used to. On Earth, the atmosphere acts like a blanket, keeping lower altitudes more temperate while higher altitudes become colder. On Io, the opposite effect is true. Extremely cold temperatures at ground level, averaging negative 260 degrees Fahrenheit, keep the sulfur dioxide vapor cool enough to form frost, while higher in the atmosphere, temperatures can scorch over 2,000 degrees Fahrenheit due to warming from the plasma torus we mentioned earlier. While a fascinating study in magnetism, radiation, and volcanology, Io isn't very inspiring as a destination for future settlers, given the difficulty in actually, existing on the surface. I hope you packed your parka, though, because on our next stop, you're going to need it. It's hard to believe how much more different Europa could possibly be from Io, and while beautifully dangerous in its own ways, at least we can cool off a bit here. While Europa is the smallest of the Galilean moons, it's still almost as large as our own moon. In photographs, it appears like a frost-covered Mars, brownish red with an icy white sheen and deep lines carved across the entire surface. A careful observer will notice on approach that despite the giant cracks lining the surface, there are relatively few craters. Relatively few of anything, actually. Europa is the smoothest solid surface in the solar system, an interesting curiosity that hints at the possibility of large bodies of water capable of refreshing and re-smoothing the surface. Like Io, Europa experiences intense tidal forces from Jupiter and her sister moons, which continuously warm and stir a vast internal ocean and move the surface ice similar to plate tectonics. Evidence for these kind of activities have come from the Hubble Space Telescope and updated data from the Galileo probe, which indicate huge plumes of ice and water vapor could be the result of gigantic cryogeysers. And if anyone is looking for the coolest word in the English language, I would like to nominate cryogeysers. These cryogeysers erupt as the result of pressure building deep within the icy surface, like volcanic geysers here on Earth, which then release that pressure by ejecting materials high into the sky. The few craters visible on the surface and data from previous missions tell us that the ice covering Europa is quite thick, averaging about 5 to 20 miles deep. Beneath that, scientists believe there is a vast ocean of liquid water, estimated to be about 60 miles deep, kept warm by those tidal forces we were talking about. Even given Europa's smaller size relative to Earth, that could mean that the ocean of Europa holds 2 or 3 times as much liquid water as our home world. The implications for supporting human activity or even extraterrestrial life in an ocean of liquid water, even if it is encased in ice, make Europa a very attractive proposal for future exploration, and the evidence for geyser plumes could make finding a sample of that ocean easier than drilling miles deep into granite-hard ice. As radiation is still a serious danger on Europa for humans, A lethal dose would be received within 24 hours. Unmanned missions will have to do for now. NASA is currently developing a mission to study Europa more closely to investigate the potential for supporting life. It's called the Europa Clipper and will conduct 45 low-altitude flybys using radar to penetrate the thick ice sheet, spectrometers, and a topographical imager. We'll leave the mysteries of the deep for future scientists for now, as we make our way farther out from Jupiter to the next moon on our journey, Ganymede. Named for a beautiful young man taken by Zeus to become the cupbearer of the gods, Ganymede is the largest moon in the solar system. If it weren't orbiting Jupiter, Ganymede would probably be considered a planet in its own right. With a diameter over 3,000 miles, it's slightly larger than the planet Mercury, though it only contains about half the mass. Its crust is composed of equal parts silicate rock and ice, and its liquid iron core has earned it the distinction of being the only moon in the solar system with its own magnetic field. That being said, this field is completely buried within the massive field around Jupiter, so it would be more difficult to detect than that of a planet. There are some interesting eccentricities of the magnetic field that scientists are still trying to unravel, but the field does generate an aurora belt with the brightening at the poles. Although about 1.5 times the size of Earth's moon, Ganymede resembles it somewhat as a pockmarked gray sphere with lighter and darker regions scattered across the surface. Giant grooves thought to be tectonic forces crisscross the planet with many prominent craters, but it's there that the similarities to our moon end. With data from the Galileo spacecraft in the 1990s and confirmed from observations of the moon's aurora from Hubble, scientists found evidence of a vast underground ocean covering the surface of Ganymede. The effect observed in the aurora suggests a conductive ocean, meaning the water is probably salty and could exist as several distinct layers of ice, slush, and liquid. But by current estimates for a moon of Ganymede's size, a water ocean that large would easily be the biggest in the solar system. Like Europa, Ganymede's sparse atmosphere consists of mostly oxygen, though it would be easy to assume that the existence of molecular oxygen is an indicator of biological life. That's where it comes from on Earth, after all. The presence of oxygen can be explained on these watery moons of Jupiter as part of a process whereby water molecules are split by radiation, leaving the heavier oxygen atoms, while lighter hydrogen is gradually blown away by cosmic wind. Human exploration, or even habitation of Ganymede, is a possibility entertained by some scientists, although even at this distance, the radiation from Jupiter is still very dangerous. A human could last about a month before receiving a deadly dose. But the next stop and the last of the Galilean moons might provide some relief in that regard. Callisto is named for a mythological nymph lover of Zeus's, and in the lineup of the Galilean moons is a bit of a black sheep in several regards. Callisto is very striking visually, and very different from any of the other moons we visited so far. In stark contrast to Europa's smooth surface, Callisto is completely covered in craters. Many of these shine bright white or gray against a dark brown or black background, making the moon almost look like a deep-field space image from Hubble. About the size of Mercury, Callisto lies relatively far outside the orbits of the other Galilean moons, and is therefore free of much of the tidal forces and planetary interactions that drive so much activity on those other moons. And as a result, Callisto is completely geologically inactive, showing no signs of any current tectonic or volcanic activity, or any evidence that any existed in the past, for that matter. Instead, Callisto's most striking feature is the sheer number of impact craters. Large, small, old, new, the entire surface is littered with them. In fact, the surface of Callisto is the oldest in the solar system, and is thought to have been formed entirely by impacts, as opposed to accretion from the materials present in the early nebula. As a result, Callisto is almost entirely undifferentiated, meaning that there aren't distinct layers of specific compositions making it up. It is possible that the accumulation of mass over time by gradual impacts generate enough pressure within to maintain a subsurface ocean, which is music to a biologist's ears, but more evidence will be required to confirm. A tenuous atmosphere of carbon dioxide surrounds the planet, so fragile that scientists estimate it would only take about 4 days for it to be blown away by the solar wind. That suggests a continuous replenishing from the frozen carbon dioxide within the crust. But the implication is that this is about as robust as Callisto's atmosphere is going to get. For all the hopeful moon tourists out there, Callisto is getting some very real attention from visionary scientists here at home with regard to possible future habitation. Callisto's relatively light radiation dosage, calm geography, and resources make it capable of supporting fuel production facilities as part of a gas station for travelers on their way farther out into the solar system, or as a home base for more extensive exploration of Jupiter's more dangerous moons. An extensive conceptual study conducted by NASA in 2003 called Human Outer Planets Exploration, or HOPE, put Callisto on the map for more detailed planning toward these goals. And speaking of maps, we have a ways to go on our tour. 71 more known moons are waiting out there for us. Not to worry though, the remaining moons are generally smaller, so we don't need to spend as much time on each. With the Galilean moons behind us, we're passing Themisto now, a sneaky little bugger. Only 9 kilometers across, it was first discovered in 1975 before astronomers lost track of it entirely for almost 30 years before finding it again in 2003. After that, we'll come up on the Himalaya group, a family of 7 prograde irregular satellites named for the largest among them. They vary in size from 3 to 140 kilometers across, and all share some common eccentricities of orbit, suggesting they all came from the same larger asteroid, probably pulled from the actual asteroid belt before straying too close to Jupiter long ago. Up next are a couple of moons with very interesting orbits, Carpo at 3 kilometers and Valetudo at 1 kilometer. These two are not on similar orbits, but share a high probability of collision with the Galilean moons sometime in the distant future, or perhaps even ejection from the solar system if a near miss disrupts their orbit. Most of the remaining satellites are small, irregular, retrograde moons, many of which haven't even been named yet. The vast majority of these were discovered from the year 2000 right up until 2018 by a team of scientists on Hawaii led by Scott Shepard using a 3.6 meter optical infrared telescope atop the summit of Mauna Kea. One notable group within the remaining set is the Carme group. These 12 retrograde satellites are grouped close together and share similar eccentricities of orbit with the Himalaya group, again suggesting a common origin. They range from relatively tiny 1 kilometer in diameter up to the 47 kilometer wide moon Carme, for which the group is named. They're also all a similar red color to the Himalaya group, which could mean that they originated from a shared fragment of that group, or were pulled from a Jupiter Trojan that strayed too close. If you're feeling dizzy after all these moons, just imagine how the poor astronomers feel after finding them all. But thanks to their dedication, we've learned a lot about how these objects move and interact with each other in space. From orbital collisions to merging magnetic fields and plasma tori, the science has sparked an intense interest in future exploration and observation, with many more fascinating discoveries to be made. I hope you've enjoyed zipping around the moons of Jupiter. Next time, we'll be looking at Jupiter's stunning neighbor Saturn and finding out more about those mysterious rings. Stay tuned. In the meantime, be sure to subscribe if you haven't already. Settle the Stars is available on pretty much every podcasting platform, and we're also mirroring our episodes on YouTube at youtube.com/edgeworksentertainment. And be sure to ring that bell so you know when there's a new episode. We also have a Patreon page at patreon.com/edgeworksentertainment, where you can get early episodes and tons of other great rewards. The support of listeners like you is what makes this show possible, and I'm so grateful to everyone who has already joined. And be sure to leave a review on your favorite podcasting platform. It really does help. Thank you all for listening, and as always, happy terraforming. Settle the Stars is a proud member of the Edgeworks Nebula, a collection of intriguing and informative podcasts from Edgeworks Entertainment.
Edgeworks Nebula.